The problems involving electric force that we've done to this point have involved only two charges. Here's charge 1, here's charge 2. The force of charge 1 on charge 2 is equal and opposite to the force of charge 2 on charge 1, and we can find that value simply by saying F is equal to K Q1 Q2 over R squared. But now we got 3. Now we want to find the force on sphere B, that's the middle one right here, due to A and C right here. We know that charge A applies a force on charge B. B applies a force on A as well, but that's for another problem. C also applies a force on B. B also applies a force on C, but again, that's for another problem. We want to find the net force on B, so let's find the force of A on B and the force of C on B, and then let's combine them. Let's draw a Freebody diagram first. Do you guys remember what a Freebody diagram is in Physics 20? It's a diagram that shows all of the forces that act on an object. So let's draw the forces acting on object B. Object A will push object B away. We'll call that FAB, the force of A on B. It pushes it away to the right. Why does it push it away to the right? How did I know that? You answered that question. Dylan, why does A push B away to the right? No? Anyone? Trez, you know why A pushes B away? Yes, they're both positively charged, right? Positive repels positive, so A will push B away. Now, B will also push A away, right? There's going to be a force this way on object A, agreed? It's equal and opposite, but we don't really care about that force, not right now at least, because we're not trying to find the force on A, we're just trying to find the force on B. So don't worry about the other forces that act. There are others, but don't worry about them. Just worry about what's acting on B if you're trying to find the force on B. Now, there's also a force of C on B. Which way does that act? To the right or left? It acts to the right as well. B is pulled towards C. We're going to call this one FCB. B is pulled towards C. How do we know that? Emily, how do you know that B is pulled towards C? Good. B is attracted to C. B is pulled towards C because they're oppositely charged. Now, C is also pulled towards B, right? But I don't really care about that one because I'm not trying to find the force on C. I'm trying to find the force on B. In another question, maybe you're trying to find the force on C, and then you got to draw the forces acting on C. But in this question, we don't. All right, both forces are to the right. Let's calculate both forces now. Let's find FAB. It's going to be found by saying K, QA, QB over R squared. That's 8.99 times 10 to the 9 times QA, which is 2 times 10 to the negative 6, times QB, which is 3 times 10 to the negative 6. And we divide that by 2 meters squared. When we do that math, we end up getting, I believe it is, my sheet's a little bit messy here, but I think it's 0.013485 newtons. And FCB found in a really similar way, KQC QB over R squared. That's going to give us a value of 0.01198 newtons. So far, so good? Now this becomes a Physics 20 question. In Physics 20, when you had a free body diagram with 2 or 3 or 4 forces acting on the same object, the next step was to say F net is equal to what? Good, the sum of all forces. FAB plus FCB. Now FAB is 0.013485 newtons. FCB is 0.01198 newtons. Do I need to include a negative in there anywhere? No? Both positive? Yeah, both positive because they're both good. Both in the same direction, both to the right. Add these up, both in the same direction. I end up getting a value of 2.55 times 10 to the negative 2 newtons. And since that's a positive value, it means it's to the right. I want you to take a look at something. Just drop your pens for a second, okay? I'll give you a chance to write this down. Notice when I sub my numbers into this last equation, KQCQB over R squared, I drop the sign of the charge in there, or that 1 Coulomb charge. If I had made that negative 1 times 10 to the negative 6, I would have gotten a negative force right there. What would the temptation have been at that point? Yes, to add the negative in there, right? And clearly that would have given me a wrong answer. That's why I don't ever want to see you putting a negative into an equation representing charge. Okay, I want a negative to mean direction. You understand that if we make a negative as a charge here, then we've got one sign convention for negative positive. And then we make a negative or positive for left and right over here, then we've got a different sign convention. And we've got to somehow reconcile those. We can do it, but it becomes confusing. So what I'm telling you to do is just drop the sign of the charge. Just don't include the sign of a charge in an equation. Figure out whether it's right or left, positive or negative, separate from the equation, and then deal with it as positive or negative based on right or left. Does that make sense? Now, I was trying to find the force on B there. If I was trying to find the force on A, I would have drawn a free body diagram for A. Free body diagram for A would have looked a little bit different. Which way would the force of B acting on A would have been? Alexis, which way would B act on A? A and B are both positive. They're going to repel each other, right? So which way is B going to act on A? To the right? Is A going to be attracted towards B to the right? Good. Okay, good. A would be repelled to the left. We'd call that FBA. What about C on A? A is positive, C is negative. Do they attract or repel? They're going to attract. So that means A would go which way, left or right? A would go to the right. FCA is to the right. Now, that's not the question here, right? Okay, that's not this question, but that could be another question. If it was, you would add these up, same way as we added these up, except that FBA would be negative, right? Not negative because there's a negative charge involved or a positive charge involved or whatever, but negative because you've got a force that's acting to the left. Right? Does that make sense? One more example, number 4. It's similar to number 3, actually, same numbers. But this time we've got charge C down below here. We want to find, once again, the net force on B due to A and C. Well, let's say A and B, they repel each other because they're both positive. That means A is going to pull or push B. If they're both positive, they repel each other, A is going to pull or push B. It's going to push it. Push it which way, left or right? Good. So the force of A on B is acting to the right. What about the force of C on B? Grace, C is negative, B is positive. Do they attract or repel? They attract, right? So if they attract, is B going to go towards C or away from C? Towards C. So we're going to make the force of C on B this way. Now we already know the force of A on B, its value. It's 0.0138485 newtons. Same numbers as in the last question, therefore it's going to be the same value of force. FCB, same thing. We don't have to recalculate that one either. It's 0.01198 newtons. Now the net force is still the sum of the forces, but I'm going to add them together differently here. How do I add together FAB and CB this time? Last time it was just one plus the other. Sometimes it might be one plus negative of the other. This time it's, Gareth? Yes, we're going to draw a vector diagram here. Good. We're going to say FAB, which is 0.013485, plus FCB, which is 0.01198 newtons. And the resultant vector is right here, and that's what I'm trying to find there. The resultant vector is the sum of the vectors. These are adding vectors together. It's just adding vectors together in 2 dimensions. So I'm going to say F is equal to the square root of those numbers squared. Gives me a value of 0.224. No, it doesn't. No, it does not. It's 1.8 times 10 to the minus 2. And theta is going to be the inverse tan function of opposite over adjacent. You're going to get a number that's bigger than 45 or smaller than 45? This opposite side is a little bit smaller than the adjacent side. So it should be a little bit smaller than 45, right? I get 41.6 degrees. Now note what I did not do with that 41.6 degrees. I did not say south of east. How come? Sorry? No, it is a vector. Yeah, it has a direction. It's not a vector. Yeah, Dylan? No, it has nothing to do with the order. Yeah, this is not a north, south, east, west frame of reference, right? This is just here's 3 charges. If you look at my paper, 3 charges on my paper could be like this, or they could be like this, or they could be like this, right? There is no north, south, east, west in this frame of reference at all. So the best we can do is label 41.6 degrees on the diagram, right there. All right? Here's your homework for tonight, and you can work on it for the next 10 minutes of class, which is exactly 10 minutes more than the last class got to work on this for. Your homework is worksheet number 7, questions number 1 and 3. Worksheet 7, not questions 1, 2, and 3, but questions 1 and 3.